Okay, thanks very much for the introduction, Barrett. And as you've already seen that, as Michel showed, that we have lots of, well, if we use, for example, pharmacological imaging to induce resting state or task-based, particularly connectivity changes, we have actually massive and regional, very unspecific effects in the brain that might partly be confounded with regional specific changes on the functional connectivity level. Therefore, I will talk today about a different method that we can, for example, use to modulate functional connectivity. Maybe although this might be driven by task-based activity, but although could be independent of this. So let me start. What is functional fMRI real-time neurofeedback? It has basically been, let me see, it works? Yeah, it works. It basically been developed from EEG neurofeedback, which is basically very simple and widely applied. Now, during the last years, although the hemodynamic signals, that is fMRI as well as fNIR signals, have been used as to train subjects to regulate regional activity. On the lower part, you see the typical technical setup of a real-time neurofeedback experiment. So the setup is actually pretty elegant, but although pretty straightforward in the end. What you do is you circulate a specific region of the brain, display this activity back to the subject in the usual experiments, and the subject learns how to control the activity. This is pretty straightforward, but what makes this a very interesting approach, and this is already indicated by this rather technical picture there, you see it's basically a loop. And this is very interesting because actually real-time neurofeedback allows to close a loop between, because we're usually using open loop approaches. What does this mean? So actually what we're usually looking at is either forward inference, that is we change either the stimulus or the behavior and then look at corresponding changes in the brain, or we basically try to change the brain by using pharmacological modulators or maybe TMS or things like that, and then have a look how does this change behavior. In the end, real-time neurofeedback now allows us to close the loop, so to have a dynamic view on the very fine interaction between behavior, corresponding changes in the brain. And this is not just a one-way approach, but it allows us to basically to sample the entire loop. During the last year, this study, so although because of it's a very elegant approach, but also because of the growing interest in the clinical application, we actually see that we have an increasing number of studies during real-time neurofeedback. I think it started around about in 2012. What we also see is that until now, most of the studies, this is shown on the, let me see, on the right part, the red studies are basically, let's call it traditional studies that basically trained fMRI activity. And we see actually that quite lots of different regions can be trained. So we see it's motor cortex regions, but all the regions in the more emotional brain, like the insula, but also like the amygdala, that have been successfully trained. And what is also important, we see that actually subjects can learn often in one session, that means around about 20 minutes of neurofeedback, they can learn to change the activity in these specific regions. If we look, for example, at the amygdala, which is one of the regions that has been often used as a target region during these kind of trainings, we actually see that healthy subjects as well as patients can usually learn to upregulate this region as well as to downregulate this region. And what is very interesting is if you look at these previous studies, you see it's usually 4 or 5 runs of the training, which are subsequence run in one session, and it usually each run takes 4 or 5 minutes. That is, you really have the opportunity within 20 minutes to change regional specific brain activity. But to this regional specificity, I will later come back again. But for the moment now, let's just assume it's very regional activity. So what makes this very interesting? So actually, what this technique now allows us is to target very specific brain regions. And what is also important as the question is this actually a functional relevance? Because if you just can change brain activity and it does not have an effect on behavior, it's somehow a nice trick, but it's not really related to the full loop in this closed loop approach. And therefore we see that actually quite a lot of studies during the last years, and this is a nice review from the last year from Thibault. We see that actually most of the studies now already found behavioral changes. What is important, this is a study we did 2 years ago on the bottom part, is that these changes are actually specific to the region that is targeted. So, for example, in this study, we trained subjects to upregulate their anterior insula over 4 runs, and we actually saw that this has an effect on emotional empathy, which is very specific for the anterior insula, however not on arousal, which is more a distributed function that's also supported, for example, by the amygdala and other regions. So we see that actually this allows us to modulate regional specific activity and at the same time to modulate corresponding behavioral changes. So the question is now, and I directly have to admit that the current literature does not allow to make very straightforward interferences about this, but let's try. So basically we now have a very nice tool that allows us to change regional specific activity, although in the absence of potential confounding effects on the underlying neurovascular coupling. And this is very much a very nice tool to also examine changes on the network level. So can we see corresponding reorganization on the network level? Let me see whether we have this. Yes, so actually we see the corresponding changes on the network level. Currently, if you want to draw conclusions about this, it's actually very difficult, and we have several issues contribute to this. One issue is, for example, if you look at the normal real-time fMRI neurofeedback experiment, you see that usually it's starting with a localizer that is used to to map a very specific brain region on the individual level. Then the usual studies, if they imply resting state, they do a resting state scan, then have several trainings runs, like 3 or 4 usually. Then at the end, the resting state is measured again. Now, independent of all of the differences we have, for example, in the analysis approaches between task-based PPI and resting state, a major difference is that we have, if we want to compare the data until now, is actually that we see that the task data is usually mostly computed online. That is, it refers to the activity or connectivity changes over the 4 runs, but the resting state data is usually assessed before and after. So we might actually measure slightly independent changes, which one might be something like neuroplasticity, whether the other might be directly related to the training itself. One thing, but nevertheless, let's try. Another thing that makes it currently very hard to compare the functional connectivity or the network changes with real-time fMRI neurofeedback studies is the low number of studies that actually employed control groups. So it's usually a sham control group, but we see that actually again from the Thibault review that actually, green are the studies that have a control group, that actually most of the studies did not have a good control group and did not have a reason. Some of the studies actually did not have a reasonable sample size to allow straightforward conclusions. So actually, what we can do or what we cannot do, let's directly start with the bad news, is we cannot make a statistical interference or inference about the network level effects of regional activity changes induced by real-time neurofeedback. Well, nevertheless, let's just try. We can just plot the data from the better controlled studies, and let's see what we find there. So what I did here is basically I plotted the activity peaks from previous studies that used the amygdala or that trained the amygdala and later reported task-based activity changes. I hope it's big enough, but it should be on these big screens. So you see basically what is nice, that it nicely overlaps with usual amygdala networks that one would expect, so particularly in the prefrontal cortex. If we now map the connectivity changes that have been reported after modulating a different region in the emotional network, that is the insula, which is also a highly connected region, we actually see that these changes somehow overlap, but just in the prefrontal cortex. So we see corresponding network changes, plus all the very specific network changes. If we now overlap this with resting state activity changes that have been reported, we actually see that obviously the resting state changes have been mostly reported in the resting state networks, including the medial temporal lobe networks. But again, we see if there is an overlap, we see it's actually in the prefrontal regions, which now basically asks the question, is this a very regional specific change? Because if we just train very big regions of the brain to increase activity, it could be just a by-effect, what we observe in the changes in the connectivity. And although for the prefrontal cortex specifically, it could be just something like an increasing effort over the training. Because this is very difficult to be analyzed in the mass univariate approaches that are usually used in fMRI data, we try to tackle this with real-time F-nurse-based neurofeedback. So what we did, we monitored the entire prefrontal cortex and fed back the signal of channel number 7. So basically this is the lateral OFC, and we actually see a nice increase in the lateral OFC, which cannot be seen in the sham group that is shown at the bottom. What is more interesting in terms of this talk here actually is if you look at all channels separately, we actually don't see a very specific increase just in the channel 7, but we actually see that actually, well, half of the prefrontal cortex actually shows the same pattern, which indicates that actually what we often infer in fMRI-based real-time neurofeedback, these very regional changes, might actually not be that regional specific at all. The good news is, however, if we plot this for the sham control group, we don't see corresponding changes. So it seems at least that these are not just changes related to, for example, a higher cognitive effort or things like that. So it's really related to the training itself, but they are not so regionally specific. Another thing we want to nicely control before we move on in the field is definitely, like indicated by this nice simulation study by Cole et al., whether the underlying activity changes might actually be the driver of the connectivity changes that we observe. So you can lively imagine if we increase activity in one region, it will definitely influence somehow the connectivity estimates. We tried now to also address this in one of our new studies, where we actually used connectivity-based feedback, that is subject learned and shown on the bottom. So we basically had a sham control group and a real feedback group, and fed forward during the sham control group the motor pathway connectivity, whereas during the real feedback, subjects were shown the connectivity between the amygdala and a region that matches very good up with the lateral OFC that I've shown you. What we observed here actually is that the subjects with the real feedback actually learned to increase the connectivity, and this is the red curve shown on the left, whereas it did not have this effect during the sham control training, which is shown on the right, which is in blue. What we also observed, and this is shown in the bottom, that the anxiety decreased during real feedback, but not during the sham feedback. And what is also important, we observed, we had a look at the activity changes, but in the end we did not observe that the activity changes were the driver of the connectivity changes. That is, we can modulate networks independent of the underlying activity changes as a primary driver. Which brings me basically to my conclusions. These are the activity changes, and we see in the end that real-time neurofeedback offers us a closed-loop approach that might allow us to really look into the dynamic change between neural activity, connectivity, and behavior. And the important thing is we can sample the entire dynamic spectrum. We just don't have to put a stimulus in the system and then measure the activity, but we can sample the entire dynamic interaction. What we also see, it allows the modulation of regional neuroactivity, and this makes it very interesting in terms of network research, that we can modulate specific regions without, for example, having to account for these underlying deficits or on the underlying limitations of pharmacological imaging, which might have an effect on neurovascular coupling. What is also nice is that in contrast to, for example, TMS or TDCS, which can basically just reach the more cortical regions, we can also reach very deep brain regions like the amygdala or like also the ACC, the subgenual ACC. So this allows us now to really target core nodes in these large-scale brain networks and examine or modulate their activity very specifically, and then have a look how does it change on the network level. What is also possible is to make something like experimental lesion approaches with this. So you can basically downregulate a specific region and so basically are more flexible with experimentally induced lesions, like it's always done with TMS. What we see, and this is just very preliminary data because we don't have the power now and the data or the number of good controlled studies to make really clear inferences about this. What is very clear, we see corresponding network level changes after modulating the regional activity changes. It seems to be task specific, but although some may be convergent connectivity changes in the prefrontal cortex. However, as I said, this is very preliminary and we just plotted the data. What we see is that the network level changes are partly independent from the activity changes, which is very important to basically make sure that this is not a by-effect that we are measuring. What is basically also nice is that we see that the changes are really related to training and not just specific to, increasing cognitive effort or maybe the rewarding effects of potential good feedback training. What we also saw when we now had a closer look at the regional distribution with fNERS is that the activity changes are actually not so specific, and this might be something that we might to tackle in corresponding and future regional activity changes with the fMRI, and this might be followed up to see actually how specific can we target core nodes. This might also be a new area for training. So for fNERS training, we are now working at a training that allows us to specifically control for effects on the other channels, while specifically training one specific channel using pattern classification. Okay, that's it. I think Barrett, you are?